This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. Got a vector addition problem, and I'm going to solve it by two methods. The case I want to show here is two vectors that are more than 90 degrees apart. I've got some other videos that show less than 90 degrees, and because this has a couple of characteristics that are really good to know when you're combining vectors that are more than 90 degrees apart. I've got A at 70 kips and B at 50 kips, separated by a 125 degree angle. Try to draw my drawing to scale as close as I can get it. First method we're going to solve is by the Parallelogram Law. And this is going to involve parallel lines and then using the law of cosines and the law of sines. What I want to know is, I want to know what the resultant of A plus B is. And then I want to know the angle from the resultant to vector A, the angle between those. So the parallelogram law, I generally use this, whether or not I solve the problem that way, but to visualize it. Parallelogram law says I draw a parallel line through the tip of each vector parallel to the other vectors. So I want to draw a line parallel to B, it would be something like that, and a line parallel to A through the tip of B, something like that. Then I connect the intersection of the two vectors with the intersection of those two parallel lines, and so that looks something like this, and that vector is the resultant. Okay, so one thing I really want to observe right now is if the angle is bigger than 90 degrees, then this resultant is going to be smaller than the biggest vector, at least, which in this case is that A vector, 70. And which is not the case when you got vectors that are less than 90 degrees apart. You generally get a resultant that's bigger than at least one of the vectors, or than both of the vectors, really. So the parallelogram law says draw those parallel lines, connect the intersection, that's the resultant. Now I want to use what I call the universal triangle, which is this generalized triangle where if I know A, the sides are lengths A, B, and C, the angles opposite them are alpha, beta, and gamma, or some other designation. And if I know two sides and the angle between them, then I can say what the opposite side is of that angle that I know. So in this case, when you got a bigger than a 90 degree angle, you have to do a little bit of geometry and supplementary angle stuff to see what I really want is this angle right here, opposite the resultant. This being the triangle that I'm dealing with. Because I know the lengths of these sides. This length is B, and it's 50. This length is parallel to A, so that makes this length 70. And so I want to know that angle there. Okay, by supplementary angles, I can extend this line of action of B, and if I've got a 125 degree angle right here between A and B, then I've got that same angle right down here, where it's like if I have two parallel lines intersected by what's called a transversal, that creates this relationship. 125 is this angle down here, meaning if this is a straight line, that this angle, the angle I'm interested in, is 180 minus 125, 55 degrees. So this angle is 55 degrees. Now I know everything I need to solve for, the resultant. By the law of cosines, the length of that opposite side, r in this case, is the square root of the two sides that I know squared, which is 50 squared plus 70 squared, minus 2 times the two sides, 50 and 70, times the cosine of the angle between them, which is 55 in this case. So I do the math and I come up with that the resultant of this one is equal to 58.18 kips. So just looking at my drawing, that looks about right. Note that it's smaller than the biggest angle, or the biggest vector. So that's one answer. Now I want to know, what is this angle between the resultant? I want to know this angle right here. Let's call it theta. So this case, I want to once again use this universal triangle, as I call it, and this time use the law of sines. Well, I can't solve for that angle directly. Really, I can right here. It's really this angle right here. But I'm going to do it another way. I'm going to solve for this angle, which is called alpha, just for this case. So the law of sines says that the law of the sine of angles and the length of the sides opposite them are related. So I would say the law of sine says the sine of alpha divided by the length opposite, which is this 70, is equal to the sine of this known angle opposite the resultant. So that'd be the sine of 55 divided by the resultant, which is 58.18. So I can rearrange this, and I get that alpha is equal to the inverse sine of 70 divided by 58.18 times the sine of 55. That works out to be 80.25 degrees. And now I know alpha, and I've got this 125 degree angle. I can subtract alpha from this 125 and get the angle I'm looking for, theta, which is equal to 125 minus 80.25, which is 44.75 degrees. Now, as I said, by the law, once again, of parallel lines intersected by a transversal, this angle is also theta. So I can check my work by taking the sine of that angle, theta, divided by the side opposite, the 50, is also equal to the sine of 55 divided by 58.18. I rearrange this and I find out that, sure enough, theta is sine inverse of this stuff, rearranged, 44.75. Once again, a problem that I can check with another method. That's the parallelogram law. A lot of people, when we take this test, they've already studied Cartesians, and so there may be a tendency, and I admit that I have it, to solve this problem with the law with a Cartesian solution. So the way to do that is, or the way that comes to me, is to set one of these vectors, as the x-axis, or I could make one of them as the y-axis. So let's take the 70 kip side and make that the x-axis. So if that's the x-axis, then perpendicular to that, I have a new y-axis. And if this is 125 degrees total, and this is a 90-degree angle, then that makes this angle 35 degrees. So I've got A is equal to 70. That's pure x direction, or 70I. B is 50, and I just need to get the components of that in the x and the y direction based on that 35-degree angle. It's pretty easy. I've got by down, so it's going to be negative, and I've got bx to the left, so that's going to be negative. Bx and by are the Cartesian components of b. So bx is equal to 50 times the sine of 35, because it's opposite that 35-degree angle. That works out to be 28.68. By is 50 cosine 35. It works out to be 40.96. Notice how I'm using 4 significant digits for my calculation for better accuracy. Now, A is equal to 70I, so I can just write this in Cartesian form. A is 70I plus 0j. B is these numbers, and I got to give them signs. Both of them are negative. Negative 28.68I minus 40.96j. The sum of those two, their components, is r. So I do all the math and I get 41.32I minus 40.96j. That's in Cartesian form. I need to get the magnitude of it. So the magnitude of r is just the square root of the sum of the squares, 41.32 squared plus 40.96 squared. And once again, I get that same number, 58.18 kips. So, got the same number twice. I'm happy. Then I want to get that angle between, so let me try to draw that. So what I've got is 41 in the x for my resultant. Draw it in green. And then I've got this exact value, by. So I've got a vector that looks like this in Cartesian. And I want to know that angle right there. Well, here I have a right triangle and I know the sides. So I know that this side here is 41.32. This side opposite is the same as by, which is 40.96. So that's opposite. 40.96 divided by 41.32 gives me the tangent. So theta is equal to the tangent, and theta is this angle that I'm shooting for. It's the tangent inverse, which is opposite over adjacent, 40.96 divided by 41.32. And once again, I get that exact angle, 44.75 degrees. One problem, two different solutions.